Here we are going to discuss about the solution of an important problem from mathematical expectation of probability. And the problem is given that x is a continuous random variable having spectrum is minus infinity to infinity. That is, the spectrum is whole real number. And the distribution function is given by capital F of x. This is the standard symbol of distribution function, or it is also known as CDF. So that expectation x, this is equal to 0 to infinity 1 minus fx minus f of minus x dx, provided this is tends to 0 as x tends to infinity. Okay, we first use here the definition of expectation. We know that if x is continuous random variable, then fx is the PDF of x, probability density function, and expectation of any random variable phi of x for continuous random variable is defined as expectation phi of x. This is equal to minus infinity to infinity phi x fx dx, provided this improper integral is absolutely convergent. This is very important word for this definition. Okay, now we use first the definition of expectation x. Expectation x is given by integration minus infinity to infinity x fx dx. Okay, and it is absolutely convergent. Right, and we now divide this integration into two parts. The first part is integration minus infinity to 0 x fx dx, and the second part is integration 0 to infinity x fx dx. Okay, here both the first and second integration, these are also improper integration. These are also absolutely convergent, since the sum is absolutely convergent. Okay, now we write these two integration as limit a tends to infinity, this is a tends to minus infinity, integration a to 0 x fx dx, and this is limit b tends to infinity, integration 0 to b x fx dx. Okay, we write these two integration in the form of limit. Here we take limit a tends to infinity, and here the range is a, and here b tends to infinity, this is 0 to b. This is a tends to minus infinity, and here b tends to infinity. Obviously here a less than 0 and b is greater than 0, because a tends to minus infinity and b tends to infinity. So we say that expectation x in the form of I1 plus I2. Okay, here this limit and this limit, we take the first limit as I1 and second limit as I2. Now we deal with I2 first. Okay, here we first write integration 0 to b x fx dx, and also we use here an important property, that the relation between distribution function and probability density function. We forget to write here in the list of result used, we add here another result. This is, we know, f dash x, this is equal to f of x. Okay, this is very important relation of CDF and PDF. This is the CDF, derivative of CDF, and this is the PDF. We use here the result, and we write this relation by using this result 0 to b, this is x, this is f dash x dx. Okay, because fx, this is equal to capital F dash x. where capital Fx, this is the distribution function. Now using the rule of integration by parts, we write here at the last residues. We know that u v dx, this is u into integration v dx minus ddx of u into integration v dx dx. Okay, this is the rule of integration by parts. And rule of integration by parts gives, here we take, this is v and this is u. So we write the result as, this is x into integration f dash x dx, and the ranges are 0 to b, and minus integration 0 to b d dx of x into integration f dash x dx, and another dx is here. So we get from here, this is x into, since we know that integration d f of x by dx into dx, this is integration d f of x, and obviously this is f of x. So we write, this is f of x minus, here the ranges are 0 to b, minus integration 0 to b, the derivative of x is 1, and integration of f dash x, this is becomes fx, and this is 1, this is dx. Okay, and now when we put the range b and 0, by putting the range b, we get here the result b into f of b, and when we put the range 0, then this is 0 because here x is present, minus integration 0 to b fx dx, and we can write this result as b into f of b minus b plus b minus integration 0 to b fx dx. This is capital Fx dx, and taking common b from this two term, we take common b, and also taking common minus b, we get 1 minus capital F of b, and this b can be written as integration 0 to b dx. Why we write this type of integration? Because the integration, if we done the integration, then the integration is x and the range is b 0, so b minus 0, and we get the above result. And the last term is integration 0 to b fx dx. Okay, and now minus b into 1 minus f of b plus, we write these two integration together, 0 to b, this is 1 minus, this is 1 minus f of x dx. Okay, we get this result from here. Now we deal with the first term of this result. The first term is given by this, we write here b into 1 minus f of b. We use here the definition of f of x. Here we write the definition of distribution function. It is also known as cumulative distribution function, CDF in short, and it is defined by capital F of x. This is equal to probability of minus infinity less x less equal to x, and which is given by, for the continuous case, minus infinity to x fx dx. Okay, so we write here, we first write this term integration 0 to b, this is fx dx. Here fx be the pdf. Okay, here we write fx be pdf of x from the first we take. And also we know that for pdf fx, we know that integration minus infinity to infinity fx dx, this is equal to 1. Okay, this is a very easy and popular result of probability, and this is minus infinity to infinity f this is fx dx, and we write this is 0 to b, this is not 0 to b, by definition this is minus infinity to b. We use this result there. Now this integration is minus infinity to infinity and this integration is minus infinity to b. So by subtracting these two integration, we get the result as b to infinity. This is fx dx. Okay, fx dx. Now here the value of x varies from b to infinity. Okay, that is the lower value of x is b and upper value is always, and all the other value of x is always greater than b. So if we write this integration in the form b to infinity b into fx dx, and we also here know that b is positive. Okay, and so we write that this is less than integration b to infinity x fx dx. Now we say that this integration is convergent. Why we say this type of word? Because we already say here these two integrations are must absolutely convergent. Okay, so this integration is a part of this integration because this is 0 to infinity, but here b to infinity and b greater than 0. So if this integration is absolutely convergent, so it must be convergent. Okay, and we now let as limit b tends to infinity, then this integration b to infinity x fx dx, this is obviously 0 because this type of integration by taking limit b tends to infinity becomes infinity to infinity x fx dx. So this is 0 because two limits are same of the integration. Okay, and we write that this is less than 0. Okay, but when we take as limit b tends to infinity. Also from the left side, it is always says that b greater than 0 and b greater than 0 and f of b, this is the integration minus infinity to b fx dx. So this is the integrating value of some point of the spectrum, and it is always less than 1 because the sum of all value of the spectrum or integration minus infinity to infinity fx dx is 1. So we integrate minus infinity to b fx dx, so this is less than 1. And by putting the value of f of b, this is less than 1 and b greater than 0, here we write that b into 1 minus f of b is always greater than 0. Okay, so from this relation, and also we prove above, here we say that this is less than 0 and this is greater than 0 because we write 0 less this. Okay, now in limiting case we take already here limit. In limiting case we use the sandwich theorem and getting the result as limit b tends to infinity b into 1 minus f of b, this is equal to 0. This is a very important result to prove our required result. So this term becomes 0 by taking limit as b tends to infinity. Okay, so finally we write our I2 as, here we take limit in the left side, so we get limit b tends to infinity integration 0 to b x fx dx, This is given by putting the value 0 here, we get integration 0 to b 1 minus fx dx. Also we take limit b tends to infinity. That is, we write that integration 0 to infinity 1 minus f of x dx. Okay, so we get the value of I2 as this. Now we deal with I1. This is I1. We take here only the non-limiting value of I1. This is a to 0 x fx dx. Okay, here we put first fx. This is equal to capital F dash x. Okay, so we get a to 0 x capital F dash x dx, and by using the rule of integration by parts, we get x into capital F of x. Here ranges are a to 0 minus integration a to 0. This is the derivative of x. This is equal to 1, and the integration of f dash x. This is equal to capital F of x dx. We get the result. Okay, and by putting the range, this is 0 minus a f of a, and the second term is as above a to 0 capital F of x dx. Okay, now we deal with the first term as we deal for I2. Okay, minus a into capital F of a, which is given by minus a into the definition of capital F of a. We use this definition, and this is integration minus infinity to a. This is fx dx. Okay, fx with the period. Now we write this integration as minus integration minus infinity to a fx dx. A is the upper range of the integration. So here we write x is always less than a for this type of integration. Okay, now since a minus is present here, so we write this integration as less than. This is minus integration minus infinity to a x fx dx. Okay, why you write? Because if we multiply this term both sides by minus, so we get minus x greater than minus a. Okay, and now from this type of integration, we see that this integration must be absolutely convergent or convergent to say. Why it is convergent? Because at first we say that the first integration minus infinity to infinity x fx dx is convergent, and this integration is convergent. So this is a part of this integration, because here the range is minus infinity to a, but here the range is minus infinity to 0, and a is always less than 0. Here we say. So this must be convergent. Now if we take a tends to minus infinity, okay, a tends to minus infinity, then this integration becomes minus infinity to minus infinity x fx dx. So we get the result, this is equal to 0. So we write in limiting case that this value, this is minus a into f of a, this value is less than 0. Okay, here a is negative. Here we say a is negative. So minus a is always positive. So minus a is positive. Okay. Also f of a is the distribution function, and the definition of f of a we get, this is minus infinity to a fx dx. Okay. So this is always greater than 0. So this term is greater than 0 and this term is greater than 0. So the product of these two terms is also greater than 0. Okay. Now in limiting case, we say that by using sandwich theorem, the limiting value, that is limit a tends to minus infinity minus a into f of a, this is equal to 0. Okay, so for this integration, the first term, this term is tends to 0 if we take the limit a tends to minus infinity. Okay, and by taking limit, we write the result here. This is limit a tends to minus infinity. This is x fx dx. This is equal to, we get the first term is 0 and the second term is minus integration, sorry, we write limit a tends to minus infinity. This is a to 0, this is minus fx dx. Okay, we get the result from I1. This is, we write I1. Okay, now we need some calculation to prove our final result as. We calculate here. Now we get here I1. This is given by this integration. Here we put x, this is equal to minus z. Okay, so dx, this is equal to minus dz. So for this integration, we write limit a tends to minus infinity. This is minus integration. A is given by, if we change the limit of integration x to z, this is a, this is 0, and a means this is z equal to minus a, and this is 0 means 0. So we get minus a to 0, and this term is capital F of minus z into minus dz. Okay, so this is limit a tends to infinity, sorry, this is minus infinity, and minus are balanced together, so we get this is minus a to 0 f of minus z dz, and we can write this integration by changing the variable, and we write that limit a tends to minus infinity, this is minus a to 0 f of minus x dx. So if we take the limit a tends to minus infinity, and we get the result as integration infinity to 0 capital F of minus x dx, because here minus a is present and we put a, this is equal to minus infinity. Okay, and this integration can be written also as minus integration 0 to infinity capital F of minus x dx. This is the value of I1. Okay, this is the final value of I1. So by adding two values which are I1 and I2, we finally write the result here. This is 0 to infinity, here 0 to infinity, and also here 0 to infinity. We first write the value of I2 first, because these two terms are addition. So 1 minus f of x, and this is given by minus f of minus x dx. Okay, and clearly we see that this is our required value of expectation x, and which is this. Okay, very important but lengthy problem of probability from the expectation. Thank you for watching.